All right, here's where we left off in our previous video. So the important thing here is our our length element formula. So I'm boxing this in red. Right now, you want to copy this formula down, either in the printout that goes with this section or in your notebook, because that is the central formula that we're going to use as we code along in MATLAB. So you want to write that formula down and then pause this video and open up MATLAB because we will do a code along. So it's important that your MATLAB is up and running. So open it, make sure that it's fully awake, that it had time to load, and then you can restart the video and do our code along. Okay, welcome back. Hopefully your MATLAB is open and ready, that it's not still spinning its wheels, getting ready to open. So make sure that it is open and ready. You want to make sure that you have a new folder to put this code in. We're going to have a couple pieces of code that we're going to work with. So this folder should be entitled line length. I put mine in my math class applications. You probably want to stick it in with the other, the volume information. You know, we had several codes about volume, and you can start a new folder about line length there. And then we want to be able to start our new code. Okay, I had a little glitch in waiting for my MATLAB to catch up with the Zoom meeting here. So hopefully I haven't lost my train of thought, but we're going to create a program called line length. All right, so make sure you type that in as the first line of the comment. Notice you want to make it one word. And now we're ready to save this program. So far, there's not much to it, but we will save as. Make sure you're in your line length folder, and I will save it as line length. Okay, some of you may find that I don't type that quickly, so you may want to play the video faster as you type along. Others of you may type more slowly than I do, so you may want to play the video at a slower speed. So you pick your speed of playback. But whenever we write a code, we should say what it does. And we should say this program, actually we don't, it's clearly a program, so we can say draws a line or a curve perhaps in the form of y equals f of x and calculates the length of the curve. Okay, so there we have it. That's what we'll do. So now we're ready to set the parameters. I'm going to add one more thing in here. We're going to say set parameters and function. All right. So we're going to do a little bit of calculating in the parameter section. We're sort of cheating. You're not supposed to do calculations in the parameter section, but it's we need to put the function in the parameter section or somewhere near the beginning of the code. So I want it to be right up front. So if we're going to plot a curve, we probably need to first of all establish what the curve will be. So let me gather my thoughts here. Okay, so it's very important that we put things in order. So if I'm going to plot of y equals f of x, I first of all need to know where I'm going to start plotting it. So in calculus, we call the beginning of an interval a. So let's just start a at 0. All right, so this will be the left side curve, and then we need a b value. Let's run that up to 5. And that will be, I'll tab to write my comment in, and that will be the right side of the curve. Okay, so we now have an interval from A to B. I've commented those. All right, and we need an n value right up front. Let's start with an n equal to 3. So this will be the number of subintervals. Okay, remember you can pause the video anytime if you're getting behind in your coding, but feel free, or speed it up if you're feeling this is taking too long. So now that we have those things, we can determine what x values that we will use in plotting our curve. So we can let x equal the linspace of a comma b. So that will go from a to b. And we're going to use n plus 1 points. The reason why, if we do one subinterval, it would have 2 endpoints. And if we do 2 subintervals, we would need to have a point in the middle and 2 ends. So that's a total of 3 points. So we always need 1 extra endpoint when we're trying to create the linspace. So these will be our x values. Right? And then I'm going to put a function in right now. Let's start with a real easy function. Let's just do y equals x dot squared. All right. Now this will give me all of the y values. So I'm doing this in the parameter section just because it's easier to compute it right after I have the x's. I can plot all the y's. That's actually a calculation, but I am going to cheat and put that in parameters. Right, then we might want to actually, just like on our TI-84, it's nice to have a window that we can change. So let's create a window of values. Let's start with x min. We'll start with -1. X max. We'll run that out to, since we're going to 5, let's go out to 6. Y min. We'll start with -1 and y max. We better make that larger than 25, it looks like. So we better go up to, we'll go to 26. So that will create a window for graphing. Okay, so let me just comment, all of these things will be the parameters for the graph window. I'll just say for max, min values for graph. Okay, so it took 4 lines of code to do that, but that will allow us to adjust those within the parameters. Oh, and by the way, I made a mistake. When I create a new section of code, I should make a double comment sign, double % sign, so that it blocks off that section of code. Okay, so at this point, we should be able to make a graph of our function. So let's go right to the plot section, right? And we'll just simply plot x comma y, and let's see what happens when we run that. Okay, so it actually worked for me. Usually the first time you run it, you find that you have some errors. First of all, before you run it, notice there's our green box over here in the upper right of the editor. That means I don't have really any syntactical errors, but that doesn't mean that it will work. All right, so here we have a little bit of a graph, all right, that we can work with. So you can see it's, it's kind of scaled in a strange way because we go from 0 to 5 in the x direction, but we're going to go from 0 to 25 in the y direction. And we didn't use these x min, x max, y min, y maxes at all. So let's go ahead and change that. Let's create an axis command. Okay, so remember, your axis command has to have a vector of values that follow the lowest x to the highest x, then the lowest y to the highest y. So we've defined those in our parameters so that we can change those without having to scroll through the code. So that is our axis command. So now we should be using those values, and you can see that our function is stuck. It goes from x equals 0 to x equals 5, but our window matches the x min, x max, y min, y max window. Other things that you might like would be to add a grid. Makes it easier to see the graph. You can run that, see what adding the grid does. Okay, it adds big blocks. I like to also add grid minor. That will add smaller divisions when I run it. All right. Now, you can see we may want to, let's add some labels. X label. It will be this simple. We'll just call it, I'm putting it in apostrophes because that's a string. We're putting in the word X, not a value for X. And we'll have a Y label. Do the same thing. We'll put in the string Y. So now when we go to graph, it adds X and Y. I don't really need the command window, so I'm going to stretch my graph out a little bit. All right, now we have other options we can do. Okay, so right now, one of the things I don't like is that I'm trying to measure length. So I really would like the scaling in the Y direction to match the scaling in the X direction. So one thing I can do for that is say axis equal. Let's see what happens when I do that. Okay, so that actually is more of the way the curve looks. All right, the curve does not run, it's much bigger in the Y direction than the X direction because we're looking at Y equals X squared. So I would expect the Y values, I want it to be much taller than it is wide. So by throwing in axis equal, it will make sure that the scaling is squared out equally in the X and the Y direction. All right, other things, I'll add a title later. But you'll notice we don't have X and Y axes right now. So let's add those in the plot statement. All right, so the first thing I'm going to do is make sure that the curve is in blue. So I will make it a blue line. So notice the X and Y values will be plotted. They'll be connected together, the X and Y pairs in a blue line. And now I'm going to put in two axes, the X-axis and the Y-axis. So to get the X-axis, I need to have a pair of X values and a pair of Y values. So I want the X-axis to go all the way from X min up to X max. And I want the Y values to go from Y min. Oh, nope, I want my Y for the X-axis, I want both Y values to be 0. So I'm going to connect the point X min 0 to the point X max 0, but MATLAB requires that you put in all of the X values that you're going to connect in one vector, and all of the Y values you will connect in a second vector. And we want to do that with a black line. All right, and then likewise, we'll want to add a Y-axis. So our Y-axis should have 2 zeros for X's, because X will always be 0, and we need to pair those with the extremes of the Y. So Y min, Y max. Okay, and we want that also to be black. You can either do dash K or K dash, it doesn't matter. So that should end our plot statement. So now we can see how that lines up on the axes. All right. If I were to make this window skinnier, you can see the X values are going away. Oh, I want the Y's of the figure to be bigger. I don't know that I can adjust the figure in as I do that. Okay, so we may try some other things with the scaling of the figure. So let's go ahead. Actually, let me do that now. So axis equal is a little bit clunky. So I'm going to turn that off. It's not working the way that I want it to. So let's see what happens if I turn that off. Okay. Now the problem is the X's are much wider than the Y's. So one way I can accommodate that is I can just move I can scale the graph myself. And the graph should actually have a shape that looks something like that. All right, so if I wanted to see what it looks like as I do it, that's more like what the function should look like because it's much taller than it is wide. So if I wanted to make a copy of the picture, I would probably do something like that before plotting it out. Okay, but let me stretch that back out. All right, so That's one way I could take care of it. Other ways I could take care of it, I could make axis equal again. But then I have a problem. Actually, let's just not do that. That's going to get, it'll get more complicated if I try to code that in. So let's just stick with this. If we want to, just be aware right now that the y increment sizes are much bigger. I'm sorry, I should say the x increments are much bigger, because if you go over about a little bit here, x only runs from 0 to 6, while y runs from 0 to 25. So we've compressed the y-axis down so that it doesn't give us a realistic length right now, unless we do what we were talking about here, where we get the figure sort of curved by moving around the window, the graph window itself. Okay, so let me just bring that back out, and let's continue with the code. Okay, so we have something that graphs in the number of subintervals we have. If we wanted this to be 2 subintervals, we would see 2 line segments. If we wanted to look more like a curve, we could do something like go to 20 subintervals. Okay, and you can see, you can't even see the lines. There are actually 20 line segments making that curve. It's hard to see them. And if we went to 200, you definitely wouldn't see individual lines. It is made up of individual lines, but they end up matching the curves so closely, your eye can't tell the difference between the lines and the curves. So let's just go back to 2 lines so that we can see those lines. And now the trick is determining the length, the total length of the lines. Okay. So how are we going to do that? Let's create another section of the code where we calculate the line lengths. Okay, so right now, the key is, first of all, we're going to do this repeatedly. So right now we only have 2 line lengths, but if I change the number of segments, clearly we're going to need to do more additions of lines. So hopefully you realize that's a loop. So let's do IT for iterations. The loop will iterate from 1 up to n times. So right now n is only 2, so it will only go through the loop twice, all right? Now we're going to have to total the line length. So before the loop, let's just make sure, because we might have something residual in memory. Let's call L, that'll equal our total line length, will be set equal to 0. All right, so this is the cumulative line length. So we need that to be 0 before we start counting. All right. I'm going to go down a couple of things right now. I have a red editing box, so I want to end my for loop, and that makes the editor happy. But now we need to put something inside of the for loop. All right. So what we need to do is we have to add a delta L. I'm going to call that DL for a little piece of L. So the first time through the loop, we're going to want to connect the first x value and first y value to the second x and second y in order to get the length. Now remember our formula for length. Hopefully you wrote it down. It's the square root. Actually, let's do this in a couple of steps. So it's going to be the square root of dx squared plus dy squared. Now that's going to cause troubles because we don't yet have dx and dy. So we need to define those right before we use them. So the first time through the loop, dx will equal x of it plus 1 minus x of it, actually each time through the loop. The first time through the loop, it will be 1. So it will take the second x value, that's what x of it plus 1 is, and it will subtract the first x value. The second time through the loop, it will take the third x value and subtract the second x value. We can do exactly the same thing for y, so that this will give us our delta y's. we'll take y of it plus 1 minus y of it. And the first time through the loop, it will take the second y value minus the first y value. And the second time through the loop, it'll take the third y value minus the second. And as we add more subintervals, it will just keep iterating that process. And we have a DL that's created just from the Pythagorean theorem. So the first time through the loop, we get the length of the first hypotenuse, and the second time through the loop, we'll get the length of the second hypotenuse. And we need to add those on to our cumulative L. So L, the cumulative length, will be assigned what it was plus DL. So we're simply, whoops, I'm sorry. Need to get out of this. Hold on, there we go. Okay, so a comment in here. So this will be the total, the summing of the lengths. Okay, so each time through the loop, we'll add another hypotenuse on to the total length. In this case, we'll just run through twice. Okay, so we're going to need to report that length. So I think a great place to report that length is in the title. Right, so notice we didn't put a title in yet. Let's add a title. Whoops, it's not capitalized. Title. Okay, so what we'll want to do is probably put a whole string together. All right, so we will want to say f of, oops, I'm going to concatenate a string. So I need to use brackets. And I will start by putting in the string f of x. Actually, this is not going to, we're not going to worry about this. We're just going to say the line length equals. Okay, so there's a string, and then we're going to concatenate to it the value of L. Oh, but we need that as a string. So we need to num to string the L value. Okay, that should do it. And let's close this up. So we have a string, just a sentence, line length equals, and then we're going to add as a string the value of the length. So let's run and see what happens. Okay, so it tells us what the line length is. Let's add one layer of complexity to this. Oh, let's see what happens. First of all, if we change some things. Oh, I must be missing a semicolon. So I have an orange box and it says I missed a semicolon in line 25. I am just going to put that in right now and just fix it. And it added that to line 25. So what I want to do now is change the n value. So we had it at 2. What happens if we make it 4? We're getting closer to having the parabola, and we can see that the line length changed a little bit. Let's go to 8. Line length changed a little bit more. Let's go to 16. And the line length, you'll notice the digits are changing further out in the decimal place. So if I only wanted to be accurate to the 10th place, 8 subintervals would have been enough. I think we're going to probably close in somewhere around 25.8. If I do 16 subintervals, you can see the 10th place changing. And if I were to double that, let's go, well, actually just go to 160. So we're multiplying by that by a factor of 10, and it barely changed. It changed out in the hundredths place. So if I went out to thousands of points, I don't even see the change. So after a certain point, the number of subintervals isn't really, won't change the precision of my calculation in any noticeable way. So you can go down to a number like 16, and you'll get very close to what the actual length of the line is. If you cut that down to something like 4, you'll see it's a little bit lower, but not by much. So it's just a little bit lower than the length of the line. I'm going to add one more thing in the title though. We're going to get fancy. We're going to add the line length for a certain number of subintervals. Right, so let's tack this on. We'll add it down on the next line. So that's what the 3 dots mean, is we're going to continue this line. And we're going to put a couple spaces in for, and then we'll put num to string n. I think it was a capital N. Was it a capital N or a lowercase n? I'm going to go back to the parameters and check. It was like lowercase n. So num to string lowercase n. Code won't know what capital N is. And then we'll put in the word subintervals. Okay, so when I do this now, the title will tell me the line length, and it'll also tell me how many subintervals I used. So we're able to calculate the length of this line in as many subintervals as we like, and that's fairly simple code. So if we ignore the code that was required to plot this, we only have, and also we had about 8 lines of code here for plotting, creating the plot window. So if we take those lines of code out, we're down under 20 lines of code are all that's needed in order to create the points for the line and to calculate the length of the line. This block of code right here is the calculus of it. Okay, we're going to simply use the Pythagorean theorem to determine the length of each hypotenuse and add that on to the running total of length, and just do it repeatedly as many times as we have subintervals. So this tiny little block of code is the brains of the operation that's doing all of the calculus. So hopefully you've been able to copy this code down. Feel free to replay the video. If you did miss parts of it, I am going to copy this code onto the sheet on which you're doing your problems. So that should finish this.